Okay, let's start this video and let's see contents first. First, I will explain some theoretical background of the Curvelet transform, and then I will introduce the Curvelab, that is the toolbox that can be used in the MATLAB, and that is provided by the curvelet.org. And then I will explain you that how you can take Curvelet transform of an image. So I will explain its MATLAB code, and then I will show you that how you can denoise a noisy image using Curvelet transform. So again, I will explain its MATLAB code. Before watching this video, I recommend you to watch my previous two videos. One video is about introduction to the wavelet theory and its applications, and its corresponding link is given in the description. And the second one is about the denoising of image using MATLAB. Its link is also given in the description. So actually these two videos will give you the idea about the wavelet transform, that what is wavelet, how it is used, and then what is denoising, then how denoising is done using wavelet transform. So that will provide the strength to understand this current video. Now let's see some theoretical background. The Curvelet transform is a multi-scale geometrical transform, so that can represent edges in curves, singularities much more efficiently than traditional wavelets. Wavelets have actually the disadvantage of the poor directionality. As you know, if you have seen my previous video, you can see that wavelets are still good in capturing the horizontal and vertical and then diagonal directions or such edges present in the images. But if they need to capture the detail along the curvature, they are not good. Okay. So although there are some improved wavelet transform later introduced, such as the complex wavelet transform that has the directional selectivity, but the problem is that they are complex. It was really difficult to design the complex wavelets and the perfect reconstruction properties and good filter characteristics. So the problems are associated with those complex wavelet transform. Later in 1999, an isotropic geometric wavelet transform, which was known as a Dirichlet transform, that was proposed by Candice and Donoghue, that was able to capture the details along the curvatures. And in year 2000, by the same authors, the Dirichlet transform based Curvelet transform was introduced. So it was called the first generation Curvelet transform that was based on the Dirichlet transform. And later, the second generation Curvelet transform was also introduced by the same authors. That was an improved version from the first generation, and it has been shown to be a very efficient tool for many different applications, such as image processing, seismic data exploration, fluid mechanics, and then solving the PDEs, that means the partial differential equations. The discrete Curvelet transform of this second generation, although it was good in representing the curve-like singularities, but it suffered with the two problems. The one is that it is not optimal for sparse approximation of curve features beyond c-square singularities, and second is that it is highly redundant. So it gives highly redundant output. But later, a fast and the less redundant Curvelet transform were introduced, so which discarded Dirichlet transform. So these fast and less redundant Curvelet transform did not use the Dirichlet transform as it was used in the first and second generation Curvelets. In this newly implemented Curvelet transform, which is also known as FDCT in short, that is the fast discrete Curvelet transform, It is implemented in two ways. By using one is a unequally spaced fast Fourier transform, that is also known as the USFFT based Curvelet transform, and then other is the wrapping function based Curvelet transform. I'm not going into the theoretical detail of this. It will be quite big to cover in this video. So for more details, you can go for the original research paper of these Candice and Donoho that is available on the internet. This wrapping based FDCT is faster than the USFFT, therefore wrapping based FDCT is widely used. Now let's see that how you find the Curvelet transform. This is the basic expression. So C is actually representing the Curvelet coefficients, which are the function of J, theta, and K1, K2. So what is J? J is a scale. Okay, so scale means the coarse and the finer and the finest, like this. That means if you remember that if you do the wavelet transform, then you define the number of decomposition level. So same is scale here. So if you define J equal to 3, it means there will be the 3 level of decomposition of image using curvelets, right? And theta is the orientation of the curvelets. So curvelets are arranged in the spatial domain like this, maybe horizontal at some angle and some other angles. So at various angles, these curvelets are arranged. So that is defined by this theta, and then K1, K2 are the spatial location of the curvelets. So that means K1, K2 for this two-dimensional these values, and K1, K2 for this different K1, K2 for this, like that. And fxy is your image of which is of size m by n, and this is your curvelet function. This is also a two-dimensional curvelet function. Okay, this equation which is in the spatial domain can be computed in the frequency domain also. That is easy, and it is implemented like this by the proposed algorithms. So for that, this equation is written here in the frequency domain. So you can see that fxy, that is image. So we find the Fourier transform of this image, then multiplied with the curvelet Fourier transform of the curvelet, and then taking the inverse Fourier transform of whole product. So you get the curvelet coefficient C for a particular scale J and orientation theta. So here in this slide, you can see the various curvelets and their corresponding Fourier transform magnitude spectrum. So these are the curvelets. So this is curvelet at the scale 1. This is the curvelet at the scale 2. Scale 2, as you go for the higher scale, your curvelets will be more sharper and sharper. You can compare these three curvelets in these three figures. So this is quite wider, and this is less in width, and it is very sharp at the scale 4. Okay, and these are the corresponding Fourier transform. So for this curvelet at the scale 1 gives this magnitude spectrum of FFT, and this curvelet has this type of wedge in frequency domain, and this curvelet gives slightly bigger, and the finest one at the highest scale gives even the bigger magnitude spectrum in the Fourier domain. And these you can see that these all three curvelets are at the same angle theta. This is also almost at the same angle. So that's why this Fourier spectrum you can see that you are getting at almost the same angle. So if I measure the angle from this x-axis, so I'm getting this theta for same for all these three wedges. Okay, so if my curvelet rotates, So suppose instead of this orientation, my curvelets has this orientations or this orientation, then obviously I will get the different theta in the frequency domain for that corresponding curvelet. So actually these curvelets in the spatial domain are arranged at various theta at various scale j, that means from coarser to finer, in such a way that entire FFT, that means this is the Fourier transform spectrum of your image, row wise and column wise. So all the curvelets in the spatial domain are arranged in such a way that this entire spectrum is covered by these frequency wedges. That means one wedge, frequency wedge, is corresponding to the one curvelet in the spatial domain, as you have seen in the previous slide. So in this figure, this red one actually is the Fourier spectrum of one curvelet in the spatial domain, which is at the scale 4 and the orientation 5. Why scale 4 and orientation 5? Because this center one, as you can see in the previous slide, that this one. So this is your curvelet at the scale 1, and at the frequencies in the frequency domain, it is giving this center square, right? So this in this figure, the same is here. So this is at the scale 1. This is at scale 1, and these all wedges are at scale 2, and this is scale 3, this is scale 4, and this is scale 5. So that's why the 5 level curvelet digital tiling is represented here, and this red one is at scale 4 and orientation 5. So you can see, obviously this is the part of this fourth ring, and orientation is 5. So we count from this horizontal axis. So this is first orientation, this is second, third, fourth, and this is the fifth one orientation. Okay. The center square, it represent actually the approximation coefficients of the image. Okay, and while these all other wedges represent the detailed coefficients of the image, that means the high frequency contents in the image. So when you move from lower scale to the higher scale, that means your curvelets are compressed, as you have seen in the previous slide. That means here you get the coarser wavelets, and at the finer level you get the wavelets, very sharp wavelets. That means they are capable of capturing very fine details available in the image at any curvature. So at scale 2, there are 16 possible curvelet orientations. So you can at the scale 2 you can count these wedges. These are 16 in count. Okay, so 1 2 3 4 5 6 7 8, like so these are 16 wedges, and at level 3 they are 16 again. So they are 16 again. At scale 4 these are 32. So these are total 32 wedges, and after that they are 64, and so on. One frequency domain wedge follows following relationship into its shape. It has width and the length, so it has a relation. So for any scale j, its length is proportional to the square of its width. Okay. Now let's see that how the Curvelet transform is how it can be implemented in MATLAB. The MATLAB actually has no function to implement Curvelet transform. So, but no problem. We have a third-party toolbox which is offered by the curvelet.org. So that you can get from its website. So when you go to its website, that is www.curvelet.org, you can get this software. So go to the software. Okay. And just simply register your account, and then you will be able to download it. It's a very small in size, few KBs. And this toolbox is known as the Curvelet 2, and its latest version is 2.12. The one good thing is that it has both MATLAB functions as well as C++ functions. So those who are interested in writing the C++ functions, so they can use it from here. Now let's see these two functions from that Curvelab toolbox. So this one is for FDCT, that means fast discrete Curvelet transform, and this is for inverse Curvelet transform. Okay, so now let's see what parameters are passed in this function. So first see this first one. This x is your image of size m by n is real. That means you need to define either 0 or you need to define 1. So if you the default is 0, so it takes a complex valued curvelets, otherwise it takes real valued curvelets. So you can use it or the real valued curvelets. And then finest. So finest means either you write 1 or 2. So at the finest level, what will be used by the algorithm? So if you write 1, that means the curvelets will be used for a finest level decomposition, otherwise wavelets will be 2. So the wavelets is actually the default. Actually it has some algorithmic values, so for more details you can go for the actual algorithm or the literature of this toolbox. And then NB scales. NB scale, that means number of decomposition level. Okay, that means you are defining the J. So if you define for example J equal to 3, that means there will be 1, 2 and 3 total 3 level of decompositions, I mean 3 scales. So 1 representing the approximation coefficients, while the 2 and 3 will represent the detailed curvelet coefficients at scale J and J equal to 2 and 3. If you don't define it, that default will be taken by this. So M or N are your image size, M or N. So a minimum of these two will be chosen, and then -3 and the log 2 after taking the log 2. Okay. So now next is NB angle scores. So NB angle scores actually that means the number of angles. That means the orientation of those wedges in the previous diagram, if you can recall, at the second coarses level. Although it is minimum value is 8, but the default is 16. So if you remember that previous image, after the center square, there were total 16 wedges. Okay, so the default is 16. And let's see that what type of output actually we get by executing this FDCT. So actually we get a C variable which is a cell array, and its format is like this. So CJK K1 K2. I will show this into the MATLAB also. So J represent actually the scale, and L represent your orientation of the curvelet, and K1 K2 they represent the number of curvelets. That means and its size varies with the J and I. Okay. So this is the example code where I will show you that how you can do the how you can find the curvelet transform of an image. So when you execute this first one UI get file, a system dialog box will appear, and there you will choose your image file. By the image read, your all pixel values will come in the img variable, converting that into the double, and then passing that imgd here in the FDCT wrapping function. So one is actually for real valued curvelets, if you remember. 2 for what? That means using wavelets at the finest level, and 3 means that means the number of decomposition level are 3. That means 1, 2 and 3 only. If you don't define it, the algorithm will take according to that the formula, which is log 2 minimum of mn minus 3, as I explained before. And now I'm extracting the approximation coefficients in this variable CA. So from this C, this is how you can access the cell array to extract that center square value, if you remember. Okay, and then since values are very high in that approximation coefficient, so I am just normalizing the values for display purpose only, and then by I am show we are showing the curvelet approximation coefficients. Okay, and in this these lines of code we are extracting all the detailed coefficients at scale 2. So as I said, by the default there will be the 16 wedges after the center square. Okay, after the center square there will be 16 frequency wedges, so k from 1 to 16, and then x is carrying all detailed coefficients one by one, so the k is varying. Okay, so 2 is representing actually the second scale, so 1 to 1k, so it will be the 1 1 1 2 1 3 1 4 until 116 in the last. Okay, so each matrix, that means each wedge is taken one by one, and just for display purpose actually they are of the different sizes, so I'm just resizing to 1 square 512 size, and then showing it as image one by one. So let's see what happens after executing this program. So let me jump to the MATLAB. This program I have already written, so by pressing this run button I will execute this program. Change the directory. Okay, it asks me to choose my image, so I'm choosing this image having a circle or one plus sign. I have taken this image purposely because it has circle, that means it has a curvature like shape, and then horizontal and vertical shapes. So let me open it. Okay, let's see these coefficients, curvelet coefficients, these white colored curvelet coefficients. These are at scale 2 at various orientation. You can see that those 16 wedges after the center square are shown here. So these are total 16 orientation at the level scale 2. So you can easily see that that how the curvelets are very efficient in capturing the coefficients along the curvature, and this is my approximation coefficients at scale 1. So that is the center square of that frequency tiling wedges. Okay, now let's see the workspace for output variable. This is the output variable C. Let me double click it, and here you can see that obviously it's a cell array, and it is giving 1 by 1 cell, 1 by 16 cell, and 1 by 1 cell. As we have done the 3 level decomposition in the fdcd command, if you remember, I put j equal to 3. So obviously we are getting the 3 level decomposition. So the first one is representing the approximation coefficient, that means the center square. So when I double click it, you can see that this is a matrix C11 C11. So it's your approximation coefficient, and then this is these are 16 those 16 frequency wedges around that center approximation coefficient square. So when you double click it, you get these 16 matrices. So that means each corresponds to the curvelet at different orientations at the scale j equal to 2. So this is the matrix at the orientation 1, and this is at the orientation 2, and so on. So total 16 orientations of those curvelets. Okay, so let me jump to my presentation. Now let's go to the denoising of an image using Curvelet Transform. So this is my normal scheme. That means I have a noisy image, then I will do the Curvelet Transform. So I will get the approximation coefficient and then various detail coefficients. Then I will do the thresholding of these detail coefficients. So approximation coefficients are not thresholded, they are passed as it is. So after collecting all those coefficients, thresholded coefficients, we will take the reconstruction by inverse transform, then we get a denoised image. So we do the thresholding either soft or hard, as I have explained in my various previous videos, so I'm not explaining here. So we'll estimate the noise level, and then we will set the threshold for those frequency wedges, I mean the detailed coefficients. So this is the MATLAB, my MATLAB program. Although this program is there in the toolbox, but I have modified it and I have removed various unnecessary lines of codes, and I have introduced lines also to make it feasible for you to use for your own project. So the first line, when you execute it, obviously a system dialog box will appear where you can choose your file. Then you can read your image, converting it into the double and getting the size of the image. Now I am defining the noise variance. So I am taking sigma as 20. Then since my image which I am reading is noise free, it's the original image, so I'm making it noisy. Okay. So this is my original image, and then defining a random matrix of normal distribution, then multiplying with the noise variance sigma, then adding this noise to my image, I am getting the noisy image. Okay. So computing the norm of curvelet. So this part you have to write as it is in your program. So this is actually similar to what sigma a square upon number of elements and then square root of it. So that is how you are estimating the noise, and then calling this FDCT wrapping function. So here the noisy image is converted into the Curvelet transform in the frequency domain, and 1 means we are using the real valued curvelets, and 2 means at the finest level we are using the wavelets. And here the number of scales are not provided, so obviously it will take automatically depending on that formula. And now we are applying the thresholding. So those computed, all the curvelet coefficients are temporarily stored in this CT, so that means thresholded coefficients. So here we are defining the loop, that means we are reading all those frequency wedges. Okay, as you can see that the loop is starting from the 2, so it means I am not taking the approximation coefficients for thresholding. As I said, we do not threshold the approximation coefficients, only the detail coefficients are thresholded. So this is how the threshold is provided, that is 3 times of sigma, and then this is simply the hard thresholding is done here. So that means your matrix multiplied with the outcome of this command. That means if CSW, that means if element is greater than the threshold into the norm, then it will be kept, otherwise it will be zeroed out. So it is similar to the hard thresholding. And then after thresholding, we take the inverse transform. Okay, so we get the image into the restored image. And here are some plotting commands. So here you can see the original image, noisy image, and the denoise image. And these 2 commands are for finding the SNR. So obviously it is when we are denoising, obviously it is better to get the SNR, so we can have the idea that how well my program is doing in denoising. So I should get the improved SNR. So let me jump to the MATLAB and let's see what will be the output of this program. So I have already written this. Let me execute this by pressing run button. So it asked me to choose my file. So let me choose this pepper and then pressing open. Okay, I get this output. Let me enlarge it. So you can see that this is my original image. This is the noisy image with the variance sigma equal to 20. You can change it You can increase noise, you can decrease noise, and then see the corresponding effect. And this is the output. You can see that how well is the output. It's very similar to the input. So the curvelet's done a very good job here. Let me see the SNR into the MATLAB window. So this is the SNR value. So here original image versus noisy image is only the 16.39 dB, and the original versus denoise is 24. So there is a quite improvement in the SNR from 16 to 24. So denoising using curvelets actually did well. Let me execute once again for another image. Let me choose this Lena image, open it, and see the output. This is the output. You can see it's the original image, noisy image, and this is the denoise image. So let me see the SNR values. So obviously the original versus noisy is 16.46, and the original versus denoise is 25.5. So it's a good improvement in the SNR. So curvelets are doing well in the denoising. So that's it for this video. Thank you.